Welcome back. In today's video, we want to find the current IS in the circuit. So we're going to apply the phasor domain analysis technique to determine that current. Here we have a circuit with a capacitor and inductor in series, well, in parallel. So we can transform. As always, before we transform, we make sure we adopt the positive cosine format. Here we have our voltage source in a positive cosine format. So we can then go ahead and transform from the time domain to the phasor domain. After we do that, we can transform our voltage source and our capacitor and inductor. So we do that. Here we should have had 1 over j omega c. So we can transform our voltage source into the phasor domain, and that is 15 times the complex exponential e to the j minus 30. Our capacitor is equal to minus j 4 kiloohms. So that's minus j all over 5 times 10 to the power 4 times 5 10 to the power minus 9 minus 9 and 4. Yep, that's it. So we can then go ahead for our inductor, and that is j 6 kiloohms. So those are the impedance for our capacitor and inductor. At this point, it's up to you to pick whatever analysis technique you want to use to determine the current in the circuit. You could apply node method. You could apply loops, but all I'm going to do is transform or combine the parallel components and then use V divided by our impedance to get the current. So that would be in a series circuit. So what I'm suggesting is that we combine. So this is our resistance R, and if we combine C and our inductor, we then get a, let's just draw it like that. So this would be the combination of our capacitor and inductor in parallel. This is R, and then we can just apply KVL, our Ohm's law, to get our current. So basically now all we have to do is just combine those. So our impedance, and let's call that equivalent impedance. So our equivalent impedance is equal to our capacitor, J4 kiloohm I should say, times our inductor, J times 6 kiloohms, and that divided by J6K minus J4K. All we have to do is combine those, and that simplifies to negative 12K times J, so that would be negative J times 12 kiloohms. So that is our equivalent impedance. So having that, we can just apply Ohm's law and divide our voltage. So here we have our voltage source. So that's Vs. So we can divide the total voltage. We can divide the total voltage by the total impedance in the circuit to get the current Is. So Is is equal to the total voltage, the circuit, divided by the total impedance, and that will be R plus our equivalent impedance, which is then equal to our voltage source is 15 times the complex exponential e to the j minus 30 divided by 1k minus j 12k. Simplify. We apply the complex algebra technique to get that into the polar form, and by getting that into polar form, we can divide very easily. So we do that, and in polar form, that is equal to, or once you convert that to polar form, you can divide. And when you divide, you end up with a coefficient or magnitude of 1.25 times the complex exponential e to the j 55.24 degrees, and that's in milliamp. So that we're still in the phasor domain. And that's the current IS. So to convert from that to the time domain, we use our phasor to time domain relationship. So we get a current of IS t, which is equal to the coefficient A, which is 1.25 times cosine 5 times 10 to the power of 4t. You can just write that as that, plus the angle of 55.24 degrees. And that's in milliampere. So just like the previous problem, we went from rectangular form to polar form by using our relationship, our complex algebra relationships. So that equals the magnitude of z. Well, try not to use z. Let's always use x. In polar form, x is equal to the following. Theta is equal to the following as well. So that's inverse tangent. Our relationship for the phasor domain to the time domain is always a e to the j theta to the time domain is equal to a cosine omega t plus theta. So that's all we used to manipulate our equations in complex algebra, or in the phasor domain, back to the time domain. So as always, you transform all time-independent sources, your capacitors and inductors, to the phasor domain. Make sure that you have your cosines or your sines, your sinusoids, in the positive cosine format. Then apply whatever technique you want to use, analysis technique, either loop, mesh, whatever it is, nodal analysis, simple source transformations, and so forth, or you call it Thevenin or Norton, and then solve for what you're asked for, and then convert back into the time domain. So had we solve for current in the time domain, it would be equivalent to solving for the current in the phasor domain. However, the phasor domain is much easier because in the time domain we don't mess around with taking differential equations of sinusoids and so forth. So the phasor domain, the phasor technique, or the phasor domain analysis technique, allows us to skip those complex manipulations and just go straight forward without dealing with any sinusoids and just dealing with linear equations. So that's it for today's video. See you in the next one. Bye.